the last class we derived the following relationship between the stagnation temperature and static temperature for a flow. So let us see what it looks like. So we showed that T0 equal to T1 plus U1 square over 2Cp. So we are looking at a flow situation, a one-dimensional flow situation. So let us say that we have a flow that is going through. So we looked at a particular point in the flow which we labeled as state 1, and at this state we know pressure P1, we know temperature T1, and we know velocity U1. So given these quantities, what we were trying to do is to calculate the corresponding stagnation temperature, stagnation pressure, and stagnation density. So this gave us the stagnation temperature. In fact, it would be more convenient to write this relationship in terms of Mach number. So if I take this equation and if I divide through by the static temperature on both sides, I can write this as T0 over T1 is equal to 1 plus U1 square over 2 Cp times T1. And if I recognize the fact that Cp is going to be 1 plus gamma minus 1, I am sorry, this is going to be gamma r over gamma minus 1, I can write this as U1 square T1. And now I recognize the fact that this gamma r T1 is nothing but square of the speed of sound at that point. So I can write this as 1 plus gamma minus 1 over 2 times U1 square divided by A1 square. Okay. A1 is the speed of sound at state point 1, corresponding to state point 1, and this we can recognize as the square of the Mach number. So T0 over T1 is equal to 1 plus gamma minus 1 over 2 times M1 square. So this is a very convenient form in which we can actually use this relationship. Okay. So once I know these three quantities, I can evaluate M1, I can evaluate T0. In fact, as we did yesterday, we want to be very specific and add subscript 1 to this to denote that this is the stagnation temperature corresponding to static state 1. Okay. So the stagnation temperature corresponding to any static state can be written, if we drop the subscript 1, I can write this as T0 over T is equal to 1 plus gamma minus 1 over 2 times M square. So this is the stagnation temperature corresponding to any static state. Okay. Now in when we wrote down the expression for entropy change, we wrote the following expression. Let us take a look at that, and we will derive the expression for stagnation pressure based on this. If you remember, we wrote down that change in entropy, or we said that change in entropy is equal to Cp times dt over T minus R times dP over P. And if you integrate this, we are able to show that S2 minus S1 was equal to Cp times natural log T2 over T1 minus R natural log P2 over P1. So this was the entropy change between any two states 1 and 2. Now if I apply this equation between state 1 and state 0, for example, we are taking the in the stagnation process, we are going from state 1 isentropically to state 0, right. So if I apply this, if I calculate the entropy change for such a process, so stagnation process takes us from state 1 to state 0 isentropically. Which means that if we apply this equation between the between state 1 and state 0, I get the following. I get S0 minus S1 equal to Cp natural log T01 divided by T1 minus R natural log P01 divided by P1. Right. Since the process is isentropic, S0 is equal to S1, so that means the left hand side becomes equal to 0. So 0 is equal to Cp divided by R natural log T0 1 over T1 minus R natural log P01, I am sorry, R is disappeared now, so minus natural log P01 over P1. And once again, if you realize the fact that Cp is gamma times R over gamma minus 1, I can simplify this equation and write the following: P01 over P1 is equal to T01 over T1 raised to the power gamma over gamma minus 1. Right? And once again, if I wish to write this in terms of Mach number, I can substitute for T01 over T1 from here. So I have T01 over T1 here, so I can substitute for that from this equation, right? I can substitute for that from here and write this as P01 over P1 is equal to 1 plus gamma minus 1 over 2 times m1 square raised to the power gamma over gamma minus 1. So given the static pressure P1, we can calculate the stagnation pressure using this relationship. Notice that this is the static pressure. Now we will again explicitly state static and stagnation pressure. So P1 is the static pressure and P01 is the stagnation pressure. It is important to realize that when we calculated the stagnation temperature, we never really made use of the fact that in going from state 1 to state 0, the process is isentropic. We never really used that information when we derived the expression for stagnation temperature. However, when we derived the expression for stagnation pressure, we are explicitly making use of the fact that it is an isentropic process when we go from state 1 to state 0, right? And that is how we arrive at this. Okay. Now the stagnation density can be calculated by using the following relationship. So P01 is equal to rho 01 times R times T01. So using this, the stagnation density can be calculated. Now let us take a quick look at the stagnation quantities and their implications on irreversibilities, work addition and heat addition in a flow. That is what we are going to do next. So we are looking at a one-dimensional flow situation. So the flow is going through, and let us say that this is state 1, and state 1 is at a static condition P1, T1 and U1. Now the stagnation condition corresponding to this is P01 and T01. These are the stagnation condition, this is the static condition. P01, T01 and rho 01, which we can calculate easily. Now the stagnation quantities P01 and T01 at this point depend upon what we did before. Okay, so two things that are important. Unlike the sonic state, the stagnation state is calculated for this static state. right. So, which means that the stagnation state is a local reference state. Because the stagnation state is calculated for a particular static state. So, it is a local reference state from that perspective. Okay. And if I take a look, let us say if I look at another point 2 along the flow direction. Now, what will the stagnation pressure, temperature and stagnation density at this point be? Will it be the same or will it be different? That is the next question. So, the stagnation condition at a given point depends upon what interaction the flow has upstream of that point. Okay. So, if in between point 1 and 2, let us say I add heat to the flow or I do some work on the flow, let us say it is a compressor, or I extract some work from the flow, it is a turbine. So, depending upon the interaction, heat or work interaction that I have or irreversibilities, the stagnation state at point 2 can be different from stagnation state at point 1. Okay. So, it depends upon the interaction that I have. So, stagnation quantities can be changed through work or heat interaction and irreversibilities in the flow. Okay, remember the stagnation process alone is isentropic. As I said earlier, the flow itself need not be isentropic. There can be irreversibilities in the flow or the flow can also be isentropic, it does not matter. Okay. Now, let us see how P02 and T02 are related. So, the static state corresponding to state 2 is P2, T2, U2 and the stagnation state corresponding to that is P02, T02. So, we want to see how P02 and P01 are related, if they are related, and how T02 and T01 are related. That is what we are going to see next. Now, notice that, or you should recall that when we calculated stagnation temperature, we used the energy equation alone for calculating the stagnation temperature. So, if you go back to the energy equation, you remember we wrote it like this. This was the energy equation that we had written down, and if there is heat or work interaction, then the energy equation has to be modified to take that into account. For example, if I have heat or work interaction, then I would write this energy equation as delta Q minus delta W, where we are following the usual convention in thermodynamics that heat given to a system is positive and work done by a system is positive. So, you can see that stagnation temperature can be changed by changing, either giving heat to the system or having a heat interaction with the system or having a work interaction with the system. So, when I do either one of this, the stagnation temperature will change. Okay. Next, we need to look at stagnation pressure. Okay. So, for example, if I add heat to the system, then the stagnation temperature will increase. Or across a compressor where work is being done on the system, again stagnation temperature will increase proportional to work, and across a turbine where work is extracted, stagnation temperature will decrease because we are extracting energy from the turbine. Right. Now, let us see how we can relate the two stagnation quantities. So, we are going to do the following. If I take these two states and recognize the fact that T2 over T1 I can write as T2 over T02 times T01 over T1 times T02 over T01. So, I have taken T2 over T1, multiplied and divided appropriately by T02 and T01 to arrive at this. Okay, that is one thing, and I can write P2 over P1 similarly. So, P2 over P1 is equal to P2 over P02 times, so did I write this correctly? Yes, times P01 over P1 times P02 over P01. So we have this relationship. Notice that in this relationship T2 over T02 can be written in terms of the Mach number, right? That is nothing but 1 plus gamma minus 1 over 2 times m2 square. Similarly, this can also be written in terms of Mach number, and these two terms can also be written like this. Okay. Now we calculate, we write S2 minus S1 is equal to or natural log T2 over T1 to the power gamma over gamma minus 1 divided by P2 over P1. Notice that all I have done here is rewritten the earlier equation that we wrote down. For example, the earlier equation looked like this. So the earlier equation, if you remember, looked like this: S2 minus S1 is equal to Cp natural log T2 over T1 minus or natural log P2 over P1, right, and Cp is equal to gamma R over gamma minus 1 So if I take the R outside and take the gamma over gamma minus 1 to the exponent here, I arrive at this equation. So what I have done is I am calculating the entropy change between state points 1 and 2 in the flow. So I am calculating entropy change between state points 1 and 2 in the flow with the objective of relating the stagnation states between these two, corresponding to these two static states. That is what I am trying to do there. So now I have this relationship, and I can substitute for T2 over T1 and P2 over P1 from here, right. And I also recognize the fact, remember we had already written down the following equations, right. We had written down the fact that P0 over P is equal to T0 over T to the power gamma over gamma minus 1. So if I use this relationship and these relationships in this equation, I can arrive at the following expression finally. I get the following expression: S2 minus S1 is equal to Cp natural log T02 over T01 minus or natural log P02 over P01. Notice that by using this relationship, we have eliminated the static states from this equation completely. So now we have an equation which relates the stagnation states corresponding to static state 1 and static state 2, right. That is why we wrote this expression like this, because this and this raised to the power gamma over gamma minus 1 and this will cancel each other and we substitute. So we are left with an equation which relates only the stagnation states. This is an extremely important equation in gas dynamics, and we will look at the implications of this equation next. So we are going to look at the implications of this particular equation. Let us rewrite that equation over here. And we are actually looking at a scenario, a one dimensional flow, or even quasi one dimensional flow is also okay, as long as we have only one velocity component. So we have a flow situation like this. This is state point 1, this is state point 2, and we can look at different scenarios. Let us assume that the flow is adiabatic, that we do not have any heat or work interaction. If there is no heat or work interaction, then what happens to the stagnation temperature? Is there any change in the stagnation temperature? Remember, any heat interaction will go into the energy equation. So if there is no heat or work interaction, adiabatic flow, so we are looking at an adiabatic flow, no work interaction. So these two conditions together will lead to the fact that T02 is equal to T01. There is no change in stagnation temperature in such a case. Right? Remember, stagnation temperature can be changed by the either by the addition of heat or by the addition of work or removal of work or extraction of work. That is the only way we can change the stagnation temperature. If both of these things are absent, then T02 is equal to T01. And from this equation we see that S2 minus S1 in this case is equal to minus or natural log T02 over T01. Now, if the flow between 1 and 2 is isentropic, meaning there are no irreversibilities, then S2 is equal to S1, and so it follows that P02 is equal to P01, correct? So if the flow, remember here the important thing is I am saying if the flow is isentropic. Between state 1 and 2, then S2 is equal to S1, right, and so it follows that P02 is equal to P01. Okay, so there is no heat interaction, there is no work interaction, and the flow is isentropic. Then we have T02 equal to T01, P02 equal to P01, which is the case in most of the kind of flows that we are going to look at. Okay. What if there is an irreversibility between states 1 and 2? So meaning irreversibilities are present. Remember, we are saying that the flow is adiabatic, so the entropy change can only be positive or equal to 0. So we have already looked at the case when it is equal to 0. So if it is positive, that means there are irreversibilities, then S2 is greater than S1, and from this equation, if S2 has to be greater than S1, there is a negative sign here. That means that P02 has to be less than P01. Okay. And if you remember, if you recall, we said earlier that increase in stagnation temperature, let us write it down, increase in T0 is possible through heat addition or work addition. And similarly, increase in P0 is also possible only through increase in P0 possible through work addition. So if there is a reduction of P0, we can say that that is equivalent to a loss of work, right? So any loss of stagnation pressure is equivalent to a loss of work or loss of energy, and so it is not desirable. Okay, so any compressible flow, loss of stagnation pressure must be avoided because that is equivalent to loss of work. So we can see that loss of stagnation pressure is equivalent to loss of work, and so must be avoided at all costs because it represents irreversibilities in the flow field which must be avoided.
Sir,
yeah.
What is the effect of here heat addition on P naught?
Effect of heat addition on P naught we can infer indirectly from this equation. Let us take a look at that next. Okay, we can only get an idea about it, we cannot calculate it exactly. Okay, let us take a look at that next. What happens if you add heat addition? So in the case of heat addition to the flow, heat addition to the flow must cause an increase in entropy, right? S2 will be greater than S1 because we are adding heat to the flow. The increase in entropy is not due to irreversibility. Even if the heat addition process is reversible, still it must increase in it has result in an increase in entropy. So heat addition to the flow makes S2 greater than S1, and as we saw earlier, T02 is also greater than T01. This is very easy to see, right? T02 being greater than 1 is very easy to see. So if you go back to our original equation, S2 minus S1 is equal to Cp natural log T02 over T01 minus R natural log T02 over T01. So this is a positive quantity, right? This is increasing, this is greater than 0, and since T02 is greater than T01, this is also a positive quantity. Now this, as you can see from here, this can either be 0 or it has to be negative, right? So that is the only way this negative sign and this will add together to give a positive number. So which tells me that heat addition can probably keep the stagnation pressure the same, or there must be a reduction in stagnation pressure, so that if P02 is less than P01, this becomes positive and we can add to this. Otherwise we cannot get an increase in entropy. This would start decreasing the entropy. Because the entropy increases in a heat addition process, we know that any increase in entropy must result in a loss of stagnation pressure. So in this case also P02 will be less than P01 because of the increase in entropy due to the heat addition. Okay, we can actually illustrate this much more clearly when we demonstrate the states graphically. Okay, but since entropy increases, P02 cannot be equal to P01. P02 has to be less than P01. So heat addition, even if you have heat addition in a reversible process, even a reversible heat addition process will cause an increase in entropy and a loss of stagnation pressure. That is unavoidable. This is what thermodynamics tells us. This is not due to any inefficiency or irreversibility in the process. So this is an extremely important consideration for combustors, because in combustor we want to add heat. So if you remember the picture of the aircraft engine that we drew earlier, the air is compressed before being sent to the combustor. So we have to add heat in the combustors, but the heat addition process in the combustor also causes a loss of stagnation pressure, which means whatever work you put in, some of the work that you put into the compressor is now being lost in the combustor because of the heat addition process. That is inevitable. There is nothing that we can do about it. Now how do we increase the efficiency of the combustion process? And you have a combustor, how do we make sure that the combustion process is very efficient? And we need to make sure that the fuel and the air are mixed thoroughly so that they can burn very well. Mixing, as you know, is also a thermodynamically irreversible process. So as you keep improving the efficiency of the combustor, the loss of stagnation pressure will also increase. So these are two conflicting considerations. How do we minimize the loss of stagnation pressure while maximizing the combustor efficiency? These are two completely conflicting requirements, and so you need to optimize. Okay? That is why I said that this equation is probably one of the most important equations in gas dynamics. Okay? Alright. What we are going to do next is, we have looked at states mathematically, we have derived equations for this. Now we are going to actually depict processes graphically on TS and PV diagrams, so that our more insights can be drawn into the process. That is very useful way of depicting the flow, and that is what we are going to do next. So, we are going to discuss TS and PV diagrams in compressible flow. So, depicting flow processes in a TV and PS diagram can be extremely useful and give us a lot of insights into the nature of the flow, irreversibilities and other things, how the states are changing. It can give us a lot of useful information, and that is what we are going to do next. So, when you draw a TS diagram, what we want to show on a TS diagram are lines of contour, lines of constant V or lines of constant P. That is what we want to show. So, these are the 4 variables that we are looking at. Okay. If you remember, we said that a one dimensional flow, each state is characterized by static pressure, static temperature and velocity. In addition, stagnation pressure and temperature. So, these are the quantities that we want to illustrate. So, let us say that we want to illustrate a state in a TS diagram. So, what we are trying to do here is we are looking at a one dimensional flow situation which look like this, and we have state point 1 in this flow, and state point 1, if you remember, was characterized by P1, T1 and U1, in addition P01 and T01. So, I want to show all this information on a TS diagram. Let us say that is the first thing that we want to do. We would also want to show all this information in a PV diagram next. First thing is TS diagram. So, to do a TS diagram, we start with first thing that we want to do is look at constant lines of constant V and constant P, and we start with the following equation. If you recall, we wrote down ds is equal to Cv dt over T plus R times dV over V. Now, if I rewrite this equation, right, I am going to rewrite this equation like this: dV is equal to V over R times ds minus Cv times V over RT times dt. Okay. So, on a TS diagram, as you can see, if I move in the vertical direction, say a direction like this, if I move in a vertical direction, what is ds? ds is 0 if I move along a vertical direction. So, this tells me that as I move along a vertical direction, dt is positive, right. As I move upwards, dt is positive. So, this tells me that the specific volume decreases when I move along the vertical direction, right. dV is negative. This is positive, 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 positive. So, that means specific volume dV is negative. So, that means specific volume decreases when I move in this direction. So, V, that is the first piece of information that we can get from this. Okay, is this clear? Right. So that is the first piece of information. Now I want to look at V equal to constant lines. And before I even do that, if I look at this, right, as I move in a vertical direction, this becomes ds is equal to 0. So I can write this as minus Cv. V over RT is nothing but V over RT is going to be, remember PV is equal to RT, so V over RT is minus Cv over P times dt. This also tells me that for a given change in temperature, let us say dt is 10 Kelvin. So for a given change in temperature, right, at low values of pressure, the change in specific volume is much higher than at high values of pressure. Okay, we will show next that pressure increases in this direction. So what this tells me is, for low values of pressure for a given change in temperature. So for example, let us denote the given change in temperature like this. So this is a change in temperature, right, at a low value of pressure, same change in temperature at a higher value of pressure. So we have used the same change in temperature in both these cases. This is dt. So for this value of dt at a low value of pressure, the change in specific volume is very high, which tells me that V equal to constant lines are bunched close together here, whereas V equal to constant lines are spaced farther apart here. So this tells me that V equal to constant lines look like this here, like this, and V equal to constant lines look like this here. So the lines are bunched close here, so that for the same dt I get a large change in specific volume here, but a smaller change in specific volume here, right. So this information we can get from this equation. Now if I say that the equation for a V equal to constant line so the equation for a V equal to constant line can be obtained from here by simply setting, if V is constant, then I simply say dV is equal to 0. So if I say dV equal to 0, then I can rewrite this equation and show that for such an equation dt ds is equal to T over Cv. This is a first order differential equation, right, dy dx equal to some function of x. So this is a first order differential equation. So this gives me the equation for a V equal to constant line. I am not going to solve this equation, we are just going to sketch the V equal to constant lines qualitatively. Okay. So we already know certain things about the V equal to constant line. This is the spacing between the lines. This tells me about the slope. Okay. Notice that at low values of temperature, the V equal to constant lines are, the slope is very small. So that means the lines are shallow at low values of temperature. As the temperature increases, the slope also increases. Slope is not constant, first of all, these are curves. Although we keep calling them lines, they are actually curves, right. Slope also changes from point to point. At low values of temperature, the lines are shallow. At high values of temperature, the lines are steeper. And the spacing of the lines looks like this. They are closely spaced here and farther apart here, right. And the slope is also positive, which means the lines are all oriented like this. Slope is positive throughout, shallow here and steeper here, right. So shallow here, positive, shallow here and becoming steeper as we go along, right. So shallow and becoming steeper as we go along, right. That is what is depicted in the figure in the left in this diagram. So if you look at the figure in the left, notice that V equal to constant lines are shown dashed, and you can see that the slope is shallow at low values of temperature, and they become steeper as the temperature increases. Okay. So all the information that we have put in, that we discussed, is shown here graphically. Okay. The next thing, this is the TS diagram. So now we know how V equal to constant line behaves. The next thing that we want to do is to see how a P equal to constant line shows. So for a P equal to constant line, using similar arguments, I can show the following. For a P equal to constant line, I can show that dt ds is equal to T over Cp. using very similar arguments. Okay. Now, if I look at this equation, once again I can say that the slope for the P equal to constant isobar is positive, and for low values of temperature once again it is shallow, and for high values of temperature it becomes steeper. That much I know. Now, if I compare the slope of this with this, which is T over Cv, which one is steeper compared to these two? I can make that also. Since Cp is greater than Cv, I know that since Cp is greater than Cv, isobars are shallower than isocores. Right. So, that information is also shown in this diagram. You can see that P equal to constant lines are shallower for low values of temperature, and the slope keeps increasing as we move up. And you can also see that the V equal to constant lines are steeper than the P equal to constant lines passing through the same state point. Okay. That information is depicted here. So, with this information any of this can be transferred over here. So, all I do is, if I have a particular P1 and T1, I can go and look at the P1. Let us say that this is my P equal to P1 line, and for the given value of temperature I simply take this T1, this is temperature T1, this is pressure P1, this is state point 1. So, the information from here P1 and T1 have been transferred here. Okay. I have to now worry about how do I get this information in here and this information in here, right, that we will do as we go along. Okay. So, this talks about P and V. Next we have to look at drawing this on a PV diagram. So, we have looked at this on a TS diagram, we have to look at this on a PV diagram next.